In algebra, we often encounter polynomials with missing coefficients. Finding these values is essential for modeling real-world data. Today, we will learn how to use the remainder theorem and graphical analysis to solve for these unknowns efficiently. The remainder theorem provides a powerful shortcut. It states that if you divide a polynomial p(x) by a linear factor x minus c, the remainder is simply the value of the function at c. This link turns division into simple substitution. Our goal is to create an equation where the only unknown is our missing coefficient. By knowing just one point on the graph or one remainder, we can unlock the entire structure of the polynomial function. Let's look at the mechanics. If we are told that dividing our polynomial by x minus 2 leaves a specific remainder, our first step is to identify c. In this case, c equals 2. We will plug this value into every x term. Once we substitute the value, we set the entire expression equal to the remainder provided in the problem. This transforms a functional expression into a solvable linear equation, allowing us to isolate the missing coefficient through basic algebra. Visually, the remainder theorem tells us a specific point that the graph must pass through. If the remainder of p(x) divided by x, c, is r, then the point c, r lies exactly on the curve of the polynomial. Changing a coefficient alters the shape and position of the graph. By solving for the correct coefficient, we are essentially pinning the graph down so that it passes through the required coordinates defined by our remainder. Let's work through a full example. We have p(x) equals x cubed plus kx minus 4. We are told that dividing by x minus 3 results in a remainder of 20. We substitute 3 for x and set the sum to 20. Simplifying the equation, we get 23 plus 3k equals 20. Subtracting 23 from both sides gives us 3k equals negative 3. Dividing by 3, we find that k must be negative 1 for this condition to hold true. To verify, we look at the graph of our completed polynomial. At x equals 3, the y value is exactly 20. The graph confirms our algebraic result, showing the seamless connection between the remainder theorem and coordinate geometry. What if there are two missing coefficients? We would need two remainders. This creates a system of equations. Each remainder provides one linear equation, and solving the system reveals both unknown values simultaneously. By plugging in our 2 points, we get two equations, a plus b equals 4, and for a plus b equals 4. We can now use the elimination method to subtract one equation from the other and solve for a first. In this specific case, 3a equals 0, so a is 0. Substituting back, we find b equals 4. Our final polynomial is simply p(x) equals x cubed plus 4. Complex problems often simplify beautifully once the system is solved. The graph of x cubed plus 4 passes perfectly through both of our target points. This dual verification ensures that our coefficients are correct and that the polynomial behaves exactly as the remainder conditions predicted. To recap, always identify your c value first, set up your p(c) equation using the given remainder, solve for the unknown coefficient, and whenever possible, use a graph to verify that the point exists on the curve. Try this if p(x) equals x squared plus cx plus 10, and the remainder when divided by x minus 1 is 15. What is c? Substituting 1 gives 11 plus c equals 15, so c must be 4. You now have the tools to solve for any unknown polynomial coefficient using the remainder theorem and visual graphing techniques. Keep practicing these steps to master algebraic functions. Generated by Vision Solve AI.